All right. Hello and welcome to this, the next lecture that we have. So this is where we're going to be talking about nuclear magnetic resonance spectroscopy, which is otherwise known as NMR, more commonly known, in fact, as NMR. It's really useful. I can't emphasize that enough. If you want to know what a particular molecule is, and so long as it contains a few select elements, so usually as long as it's like biological or organic matter or some sort of pharmaceutical or a polymer or really pretty much anything, you're going to be able to determine what it is using NMR spectroscopy. It is probably the most powerful tool without question because of its kind of reliableness. Its reliability is so high compared to the other techniques. I mean, we've talked about UV vis spectroscopy. We saw that was not really very good for qualitative analysis. It was good for quantitative, very good for that, you know, whenever we want to find out how much of something there is. But whenever we're talking about qualitative analysis, identifying something, UV vis wasn't particularly good. FTIR was much better than UV vis because of the way that it looked at the bonds in a particular molecule, but it's relatively complicated. There's a lot going on in those spectra. There's a lot of overlapping peaks. A lot of very useful information there, especially about the individual environments of the different groups on the molecule, you know, like maybe a CH3 methyl group, or maybe a carbonyl group, or maybe a, you know, an oxygen here, a nitrogen there. We can pick those up on the FTIR and we can see how their interactions change with their environment. Like we could change the solvent, we could see how the peaks change, things like that. And it's useful in that sense if we're, like, for example, looking at cosmetics or something, and we want to model them using different compositions or something like that, we can see how the peaks might shift. UV vis can be used like if you're doing a sunscreen or something like that. But NMR, it will just give you all of the like individual atoms there. Like if we're doing a hydrogen NMR spectrum, oh, so that's another thing. We'll talk about that in a little while. Whenever we're doing a measurement, an NMR spectroscopy experiment, we're usually just looking at one nuclei at a time. And so typically that nuclei is hydrogen, although you can do carbon, you can do phosphorus, you can do nitrogen even. You could even do things like oxygen and stuff, although that's a much more advanced technique. But typically you're looking at one of those nuclei and you're trying to assess how many of them there are in the spectrum. So imagine you've got your FTIR spectrum, you've got all the CH bonds, you've got all the CO bonds, you've got all the HH bonds, you've got all of the bonds at once. In NMR, you can kind of filter your spectrum. So whenever you're doing the hydrogen NMR, you're only going to see the hydrogen atoms. You're not going to see the carbons, you're not going to see the phosphorus, you're not going to see the nitrogen or anything else. And this means that whenever you're looking at that spectrum, you're able to just kind of focus in on those atoms, and then they will be shifted, they'll be moved to a certain point in the spectrum, which will be representative of the kind of class of hydrogen atom they are. Whether they're hydrogen atoms attached to a carbon, whether they're hydrogen atoms attached to a nitrogen, whether they're hydrogen atoms attached to even a silicon atom, that kind of thing. And so you're able to assign them with much more reliability. It's much easier. You can just look up a table of data and very reliably you will find the peak positions of reference. Like I said earlier, this technique has been around since about the early 1950s as a commercial technique. It has changed some over the time that it's been available commercially, but by and large, it has remained from day one of the most important tools in the chemist's toolbox. It's very rare that something gets adopted and utilized so widespread so quickly in chemistry. Usually chemists are very wary of change, and they need a lot of evidence to before they adopt something. But with NMR, it was so powerful, it was so obviously good that it was adopted very, very fast. Anyway, let's talk about the fundamentals of this today. So nuclear magnetic resonance. So NMR is a physical phenomenon involving the interaction of atomic nuclei placed in an external magnetic field with an applied electromagnetic field oscillating at a particular frequency. Magnetic conditions within the material are measured by monitoring the radiation absorbed and emitted by the atomic nuclei. So what does that mean? Well, so there's this kind of like phenomena that happens whenever you place, okay, let's go back. So in NMR spectroscopy, unlike UV vis and FTIR, which we're looking at energy levels within, or electron energy levels, we're now looking at the nuclei. We're no longer really interested in the electrons. We're primarily focused on the individual nuclei of different elements. Usually the one that's most commonly used is hydrogen. Carbon's also very commonly used, phosphorus and nitrogen as well. So what happens is if we place those nuclei inside of a strong magnetic field on the order of a Tesla or thereabouts, this magnetic field can create a split in the energy levels of the nuclei. So normally the nuclei has an energy level which is just uniform for everything. It's kind of degenerate. But if we place it in a strong magnetic field, we can get a split in that energy level. And this was something that Werner Pauling from Pauling Electronegative, or no, yeah, Werner Pauli from the Pauli exclusion principle came up with. He postulated this back in the 1930s, and he was saying like he recognized that there was the opportunity for nuclei energies to interact with a magnetic field and to split, basically. And so it was found out in about 1946, about 10 years later, that this was in fact true. And then those people won the Nobel Prize for their work. But basically, you put the nuclei or sample in a strong magnetic field up to about a Tesla, and then pass typically an oscillating electromagnetic field, usually a radio frequency field now, which will interact with the nuclei. It will be absorbed by the nuclei, and then that will cause an energy change within the nuclei, well, a population change within the nuclei from the lower energy to the higher energy, and that will create enough of a signal that can be detected by the detector. So it's a similar principle. We've got two energy levels. We're looking at the gap between them, and we're trying to see if we can measure that. So in that respect, it's kind of similar to the others that we've looked at. This time, though, instead of it being electrons, we're now looking at nuclei. So if you can imagine that the nucleus inside of the magnetic field has a certain dipole moment associated with it. So it processes about an applied field here, which is our magnetic field. So the magnetic field, if you know a magnet or whatever, it has a north and south pole. So it points in a certain direction. So depending on where you're pointing the magnet, you know, the north is pointing in a certain direction. So we apply the magnetic field in a certain direction, going from one pole to the other. And the particle, the atom, is spinning in a certain, because it has the property of spin, and then it's pointing in a certain direction, the magnetic dipole moment that it has. This then has some degree theta between it and the applied magnetic field, which is called the processional orbit, which is this dashed line here. So what's happening here is that there is going to be some sort of interaction between our spinning particles magnetic dipole. The spinning particle could be an atom, and then that is going to interact with the applied magnetic field in some way to gain or lose energy. So this angular momentum and angular velocity, which is pointing in a certain direction, is called the processional angular velocity. And so this angular velocity, given the letter omega, is equal to gamma times b, b being the magnitude of the applied magnetic field, and gamma being the gyromagnetic ratio, which is just kind of an individual species-specific kind of proportionality constant. So it's really just looking at how much of the applied magnetic field does the particle actually interact with the so how much of the applied magnetic field, which is customarily given the letter B, how much of that does our particle interact with? Now, if we divide by 2 pi, if we divide this by 2 pi, we get what is called the Larmor frequency. And so this Larmor frequency is nu0, which is equal to gamma B0, B0 being the applied magnetic field, over 2 pi. And so this is the Larmor frequency here. And so this is the classical depiction of what's happening to the nucleus in a magnetic field. So for as long as a particle is spinning in a magnetic field, it can have a processional angular velocity sort of depicted like this, or described like this. And then it can also have a Larmor frequency, which is described like this, which is the processional angular velocity divided by the Larmor frequency. So that's for the classical picture. There's also a way to look at it in terms of the quantum picture. And the reason why I'm showing you both of these is because they both give exactly the same answer. And it's one of the powers of this technique is that it can be described using both. So whenever we place our particular, so if we look over in this diagram here, whenever we have a certain energy applied, so this energy in this sense is going to be our energy of our orbital, or not our orbitals, our nuclei. So in the presence of no magnetic field, we have no splitting of our energy levels. They're all degenerate. They're all sort of like at some arbitrary value, which we have listed as 0. Now, if we apply a magnetic field B0, which is our magnetic field, the one that I talked about being necessary to create this sort of split in the energy levels, we create two new energy levels, one where the magnetic moment is spin down and one where the magnetic moment is spin up. So this is from the magnetic quantum number M, which hopefully you came across in your physical chemistry. Basically just the magnetic quantum number. So the difference in these the energy of these levels is given this value and this value. Now, the important takeaway here is really that the difference in these energies is this one. This is the important one here. Because like what we had with UV vis, like what we had with FTIR, we're looking at the energy difference between the different, what do you call this? Between the different energy levels. And so those energy levels have an energy associated with them. So the difference between them has an energy associated with it. And that energy then can also be, since we know Planck's relationship E is equal to h nu, we can in fact relate that to a frequency. If we divide it through by this, we would be able to get this in terms of a frequency. So here what we have is gamma is the gyrometric ratio, similar as before. H is Planck's constant, pi is just pi, B is the magnitude of the applied magnetic field. And so hopefully what this might show you is that really the energy difference here is totally proportional to the applied magnetic field strength. So the stronger the field gets, the greater the splitting there is. And this is going to be important later on when we're looking at applications of this. Really the only thing, so we've got the species dependent gyromagnetic ratio here, and we've got two constants, H and pi. The only thing which is actually variable here is the the magnetic field strength. So this magnetic field strength, if it gets stronger, the splitting consequently also gets stronger. Over here, we just have the depiction of the dipole moments mu for spin down and spin up cases. So spin up, the vector points up, spin down, the vector points down. They are identical except that they point in precisely opposite directions. So nuclear spin and the splitting of energy levels in a magnetic field. So subatomic particles, electrons, protons, and neutrons can be imagined as spinning on their axes. In many atoms, such as carbon-12, these spins are paired against each other, such that the nucleus of the atom has no overall spin. So there are as many spin up as there are spin down. However, in some atoms, such as hydrogen and carbon-13, the nucleus does not possess an overall spin. And so for the rules for determining the net spin of the nucleus are as follows. So this is kind of going back to our electron filling way back in sort of like, I don't know, general chemistry 1 or like just basic chemistry. So if the number of neutrons and the number of protons are both even, then the nucleus has no overall spin. If the number of neutrons plus the number of protons is odd, then the nucleus has a half integer spin, i.e. 1/2, 3/2, 5/2, etc. If the number of neutrons and the number of protons are both odd, then the nucleus has an integer spin, i.e. 1, 2, 3. So an example of this is hydrogen. So I'll just do hydrogen as the easiest one. So if we look at that, so that's so it's got one proton in its nucleus. So one proton, it has 0 neutrons. So in this case, the number of protons plus the number of neutrons is odd because 1 plus 0 is equal to 1. So number is 1. And so we have nucleus has a half integer spin. So it would have 1/2 spin. Because 1 times a half is a half. The number of neutrons, so if it's both odd, so if we had like, for example, deuterium has, I don't have a space. Deuterium here has got 1 proton and 1 neutron. So that's, deuterium is a isotope of hydrogen. So it would have a, so 1 plus 1 is equal to 2. So it would have an odd, or sorry, an even number of total, but but this is an odd number and this is an odd number. So since they're both odd, the nucleus has an integer spin, and so it's going to be a value of 1 for the spin. So the overall spin L is important. So quantum mechanics tells us that a nucleus of spin L will have 2L plus 1 possible orientations. And so a nucleus with spin 1/2 will have 2 possible orientations, spin up or spin down, plus, so 1/2, so okay, how is that calculated? So 2L plus 1, it's really just the number of ML levels, the magnetic quantum number levels, if you remember your orbital filling from way back. So 2L plus 1, so 2 times 1/2 is going to be, what is that? That's going to be 1, 1 plus 1 is 2. So our ML values are going to be 2. So that means we have 2 possible orientations. We have spin up and we have spin down. So a nucleus with spin 1/2, like our hydrogen up here, will have 2 possible orientations, spin up and spin down, which we already saw on the previous slide. In the absence of an external magnetic field, these orientations are of equal energy. If a magnetic field is applied, then the energy levels split. Each level is given a magnetic quantum number, M. So you came across these before in terms of looking at the, what do you call this? In terms of looking at the electron filling of your orbitals. So in the deuterium atom, 2H, with 1 unpaired electron, 1 unpaired proton, and 1 unpaired neutron, the total electronic spin is equal to 1/2, and the total nuclear spin is equal to +1. So +1 because you got 1/2 and 1/2 is equal to 1, and then here you've got 1/2. So the electron spin is 1/2, nuclear spin is 1. So Two or more particles with spins having opposite signs can pair up to eliminate the observable manifestations of spin, so the total nuclear spin will be equal to 0. An example of this is helium. In NMR, in nuclear magnetic resonance, it is unpaired nuclear spins that are of importance. So that's we usually get unpaired electron spins whenever we have an uneven number of protons and neutrons. So a nucleus with an odd number or an odd mass number has a nuclear spin. So, sorry, an odd atomic number or an odd mass number has a nuclear spin. So hydrogen 1, carbon 13, these have odd mass numbers, so 1 and 13. And so they're both useful in NMR. Carbon 12, not so useful. Carbon 13, very useful. Thankfully, most carbon-based systems have enough carbon 13 in them naturally that you can use carbon 13 NMR. Usually, like, I mean, the abundant isotope of carbon is carbon 12, but there's a sufficient amount of carbon 13 present that you can actually measure that as well. So the spinning charged nucleus generates a magnetic field. So in the case of a proton in the magnetic field, if we have like an odd number, so if we actually have nuclear spin, like in the case of our hydrogen, it creates its own magnetic field because it can have a particular dipole direction. So we're given, magnetic fields are typically given the letter B. This is just B, not B0. B0 is the applied magnetic field. This is B, this is the proton or the nuclei's magnetic field. So here's the nucleus. It is a proton and it is spinning in a certain direction. So what's happening is the spin is spin up in this case. And so the magnetic field is going in this direction. And then because it's a magnetic field, it has this kind of property here. So it loops, the current loops around like this. And so it goes from the top, the North Pole down to the South Pole. So here is how the current is passing. It's going like this. And so the loop of a current in a particular circuit. And then here is a bar magnet where we have a North and South Pole, which is analogous to what's happening with the spinning proton. It's not exactly the same, but it's a good way to kind of visualize it. So the magnetic field of a bar magnet, if you got like, for example, iron filings and got a bar magnet and set them on the table, the iron filings would sort of like splay out in this kind of a shape. You could actually see the magnetic field on the desk in front of you if you had a simple bar magnet and some iron filings. So, okay. So if this new proton has a magnetic field, then that is the magnetic field which is going to interact with the applied magnetic field that we will have from our NMR spectroscopy. So the external magnetic field. When placed in an external magnetic field, spinning protons act like bar magnets. So here we have the external field. Here we have our bar magnet. So if we place our proton or our bar magnet like this, it will immediately orientate so that the different poles match up. So north attracts south, south attracts north. If you've ever had two bar magnets, you try to put the same pole together, there's a lot of force to stop you from doing that. But if you align them properly, so it's north, south, then you will get an alignment with the applied external field, and you will end up with your nuclei or your bar magnet aligning with this applied nuclear or applied magnetic field, and you'll end up with a very stable situation. So this is lower energy, more stable. Now, if you try to flip that, you get a higher energy, less stable situation. So this is where you're trying to point the north against the north. And if you've ever, you might have done this before, it's not such an uncommon thing, where you can like try to push the two poles of the same magnet together. Normally I'd have a demonstration in class, but we're not in class, unfortunately. You point the nuclei or the north poles together, and they don't really want to be close together. They repel each other quite strongly. And so this is higher energy, it's less stable. It wants to flip back to this situation here. So that creates two energy states. It creates this energy state, which is stable and lower in energy, and it creates this state, which is unstable and higher energy. So two magnetic fields of the spinning nuclei will align either with the external field or against the field. A photon with the right amount of energy can be absorbed and cause the spinning proton to flip. So if we give, so this is where our external energy comes from. This is where our electromagnetic radiation, the electromagnetic radiation that we'll use in most instances of modern NMR is radio frequency. So if it has the right energy, which corresponds to this energy gap, which I talked about before being analogous to the UV vis and the FTIR, the only difference being that now we're looking at the nuclei rather than the electrons. So if we go from the lower state, the alpha state, to the beta state, which is the higher energy, in the presence of an applied magnetic field, then this energy gap has some energy associated with it, and that is corresponding to some frequency. And so since that means that we can use some frequency of light to enact this change. So some nuclei and their paired and unpaired electrons, or sorry, not electrons, protons and neutrons. So here we have just the regular hydrogen, we have deuterium, we have phosphorus, we have sodium, we have nitrogen, we have carbon, we have fluorine. So or carbon-13 and fluorine-9, fluorine. So the ones here with half integer spins are ones which are going to be the most useful in our NMR experiments. These are the most common: hydrogen, phosphorus, carbon-13, and fluorine. These are the four which are measured most routinely. Deuterium is used as a kind of a mask. So what I mean by that is, like, if you change the deuterium, or sorry, if you change the hydrogen atoms in your molecule with deuterium atoms, then by and large, you haven't changed the chemical identity of the molecule so much. And you changed the kinetics for sure, but you haven't changed the chemical identity. It's still basically the same thing, but the kinetics have changed. And it's also changed the net spin to be 1, which means that it's going to be largely invisible to our proton NMR, which means that we can kind of cut it out of the spectrum if we want by replacing the hydrogen on our molecule with deuterium. I made that sound a lot easier than it is. It can be quite easy in certain cases, and it can be very difficult in others. Sodium NMR, not so commonly done because, well, there's not really a lot of sodium compounds which are particularly interesting. Nitrogen NMR is done sometimes, but it's really, you can usually get enough information out of the other types of NMR, like carbon-13 or proton NMR. But you don't really need to do nitrogen NMR because it doesn't really have any spin. You don't really get much of a spectrum out of it. Okay, and then isotope percentage. So basically all of the hydrogens in the universe are protons. Very few of them are actually deuteriums, but enough of them are deuteriums that we can actually get reasonably high amounts of deuterium. Then carbon-13 is 1%. That's really a very high percentage of a stable isotope, which is why it's possible in our samples to actually just measure carbon-13 without having to really do anything particularly different to our molecule. We can just kind of measure carbon-13. Here are some of their gyromagnetic ratios on the right-hand side, and here is the expression of what we were talking about earlier for maybe one of those calculations. If we got the gyromagnetic ratio for, this is the gyromagnetic ratio calculation for the proton NMR in the presence of 1 Tesla magnetic field. So you can see that if we put these values in, we get this value out, if you were given all those values. Okay, so how does the process of this absorption happen by the processing particle? So we've already established that by placing a nuclei in a magnetic field, we can get this separation of energy levels. That's kind of just been, it's an assumption, and it's a phenomenon which can be observed. There's no other way about it. We can observe it. So it can go through this. It also has a magnetic field intrinsic to itself, which we've also seen is possible because of the spin number. We'll mostly focus on Proton Nmr here because that is by far the most common form, and it is also incredibly useful. So there are two spin states for the proton nuclei when it's in a magnetic field. There is spin up and there's spin down. Spin up, the energy, typically it's going to align with the magnetic field as a lower energy state. So you can see the dipole moment here, and the electric or the magnetic field is going in this direction. So that is aligning with the magnetic field, is spin up. And then we have a second energy state, which is going to be spin down, where it is aligned against the magnetic field. And so that is going to be a higher energy state. So in order to go from the low energy state to the high energy state, we need to absorb some radiation. And in order to go back, we need to emit some radiation. So when radio frequency energy is absorbed by a nucleus, its angle of precession, theta, must change. Hence, we imagine for a nucleus having a spin quantum number of 1/2, so this is like the proton, that absorption involves a flipping of the magnetic moment orientated in the field direction to the opposite direction. So it absorbs some radio frequency energy, and it goes from the spin up state, which is aligned, which is lower energy, to the spin down state, which is aligned against the applied magnetic field, and is orientated in the opposite direction. So for the magnetic dipole to flip, there must be a magnetic force at right angles to the fixed field that moves in a circular path in the phase with the precessing dipole. The magnetic moment of circularly polarized radiation of a suitable frequency has these necessary properties. That is, the magnetic vector of such radiation has a circular component as represented by the dashed circles, the dashed circle here. So the magnetic moment of a circularly polarized radiation of a suitable frequency has these necessary properties. That is, that it is a magnetic vector of such radiation that has a component as represented by the dashed circle. If the rotational frequency of the magnetic vector of the radiation is the same as the precessional frequency of a nucleus, absorption and flipping can occur. So basically what this means is that there is going to be an energy difference between these two states. The energy difference is going to be, instead of being described as kind of like the frequency of the gap, energy gap, it's now based on the rotational frequency of the spinning of the nuclei. But the principle is the same. There is an energy difference, delta E, and that energy difference is equal to h nu being the frequency, that frequency being the radio frequency energy, which will be applied to the nuclei when they're in the magnetic field. If there is no magnetic field, there is no splitting of the energy levels. And if there's no splitting of the energy levels, then there can be no there can be no flipping. I mean, what this really means is like, if we think about back to the external field diagram that we gave earlier, if there's no external field, there's no flipping, there's no being opposite to the applied magnetic field, if there is no external field. So the population difference between those that are in the higher energy and the lower energy states can be described by Boltzmann Statistics. We saw this back in atomic spectroscopy. Our Boltzmann statistics, where we have two energy states. We have a higher energy state and a lower energy state, and that's equal to E to the minus E over KT, where E is the energy difference between the spin states, K is the Boltzmann constant, and T is the temperature in Kelvin. At 298 Kelvin and 4.69 Tesla, N minus over N plus is equal to this. So you can see that basically the populations are identical in both states, because this is a ratio. So the closer this is to 1 indicates that the populations are going to be equal in both spin up and spin down. So you can see that there's very little difference. Here is just another diagram of what we've been talking about. Here it is depicted as kind of like a traditional bar magnet, where we have our lower energy state here on the left-hand side, where our nucleus has its dipole aligned with the magnetic field. So you can see it goes south is aligned with north, north is aligned with south. We can see here. So if we absorb energy from our radio frequency electromagnetic radiation, then we can flip this to a higher energy state. And then this is obviously not very stable. And so it releases energy back down to this state here. And then this is what it looks like in terms of the nucleus and the nucleus's magnetic moment, which is depicted with this line here. And then this dashed line is the applied magnetic field. And the dashed circles are the rotational frequency. So here we have an absorption event, which happens and then from whenever the radio frequency electromagnetic radiation is absorbed by the nucleus, if it is of a correct wavelength, which corresponds to the energy required to flip between these two states. And remember, that energy is proportional to the strength of the applied magnetic field. Because if we remember back, it was the gyromagnetic ratio is equal to, so the angular momentum is equal to the gyromagnetic ratio times the applied magnetic field. And then we had the Larmor frequency, where we had worry about that. We had the Larmor frequency here, which was equal to the gyromagnetic ratio, B0 over 2 pi. So this then can be flipped on the absorption of that energy, and then of course it relaxes or releases energy to go back to the original state. So the relaxation process. So how do nuclei in the higher energy state return to the lower state? Emission of radiation is insignificant because the probability of re-emission of photons varies with the cube of the frequency. At radio frequencies, re-emission is negligible. We must focus on non-radiative relaxation processes. So this is the thermodynamics. So ideally, the Nmr spectroscopist would like relaxation rates to be fast, but not too fast. If the relaxation rate is fast, then saturation is reduced. If the relaxation rate is too fast, line broadening in the resultant Nmr spectrum is observed. So we want kind of a halfway house. We want it to be fast, but we don't want it to be fast. So we need to sit somewhere in the middle. And so there are two major relaxation processes which happen, both of which we'll measure. There is spin lattice, longitudinal relaxation, and spin-spin, which is transverse relaxation. So these two relaxation processes are what we're actually going to measure, because the re-emission of the photons is very unlikely. So spin lattice relaxation. So this is a T1 process. So the net magnetization, which is M0, lies in the z-axis. The z-axis is the one which points along the same axis as our applied magnetic field. So our applied magnetic field is B0. This is also our, what is that? This is also our z-axis. So z, that's in the same direction. The time constant, which describes how mz returns to its equilibrium value, is called the spin lattice relaxation time, which is T1. And the equation governing this behavior as a function of time t after its displacement is mz is equal to m0 times 1 minus e to the minus t t1, where t is the time and t1 is the position at which we reach the midpoint on this curve here. This is just first order kinetics. It's just a normal exponential graph, where m0 is the maximum value here. So there's two processes. There's the spin lattice relaxation process, which is called the T1 process. And then there's the T2 process, which is the spin-spin relaxation process. So there's just two processes. That's what you need to remember. There's a T1 process, which is spin lattice, and a T2 process, which is spin-spin. So the time constant, which describes the return equilibrium of the transverse magnetization, mxy, is called the spin-spin relaxation time, T2. And so that's given the equation here. So what we will hopefully also have noticed is that these m values are mz, in the first one, the T1, and here they're mxy, and that is going to give us the full Cartesian coordinates, x, y, and z. So two factors contribute to the decay of the transverse magnetization. So there is molecular interactions, which leads to a pure T2 molecular effect. And there are variations in the applied magnetic field, B0, which said to lead to an inhomogeneous T2 effect. And this combination of these two factors is what actually results in the decay of transverse magnetization. So molecular interactions, so interactions of the species with something else in the sample, and variations in the applied magnetic field because maybe it's not totally constant all of the time. Okay, so that will do us for today.